In this section, we're going to introduce vectors and vector equations and talk about how vectors are related to linear systems and solving linear systems as we saw in the first two sections of this course. So first, we're going to introduce what a vector is. A vector for us is going to be a matrix with only one column. We often denote this with U and V, V for vector and U is close to that. And also we're going to have a boldface V or a V with an arrow above it. Both are going to be acceptable. We're often going to be doing this boldface V for most of the stuff that we do in this course. When we talk about a vector, especially in a physics kind of concept, a vector is something that has a direction and a magnitude. With the idea of magnitude, for us, we're going to think about length. It's the length of the vector. But more importantly, a vector does not have position. It gives us two things, a direction and a magnitude, but not a position. We're going to see that in some drawings in this lecture. So another introduction here before we jump into some more examples. The set of all points in the xy plane is given by R2. Here, R, with the two lines there, is the set of real numbers. Sometimes this is just denoted with a boldface R. So when we think about R2, we're saying all the things that we can have with two real numbers, the xy plane. And in general, the set of all points in n space is going to be R to the n. So a vector in R to the n, that's where these vectors are going to lie, is a vector with n entries. Those n entries are real numbers. That's why we have n real numbers. And we're going to denote those entries v1, v2, all the way to vn. Geometrically, we can depict vectors in R2 in the xy plane or in R3 in the xyz coordinate axes very easily because we can draw things in R2 and R3. So an example of that, the vector xy is going to be associated with the point x comma y in the plane. So for instance, if we have the vector 2, 4, this corresponds to going over 2 units in the x direction and up 4 units in the y direction. Corresponds to that point right there. And we're going to draw an arrow from the origin to that terminal point 2, 4. Same thing if I have 3, negative 1. That's going over 3 units in the x direction and down 1 unit in the y direction to give us our terminal point. When we're thinking about a vector is going to start with an initial point and it's going to go to a terminal point. Since a vector does not have position, we can start that initial point wherever I want. So we're commonly going to start that at 0, 0, because that's the nicest point to start with, and then the terminal point would just be the coordinates of the matrix, the x, y. But note that I can draw these vectors wherever I want. So this vector 3, negative 1, I could also just draw over here. It has a direction and a magnitude, and I can draw that vector wherever I want in 2 space, and it's still the same vector. But it's going to be called in standard position if I start it at 0, 0 and it goes to that terminal point. When we're thinking about vectors, we're going to think about adding vectors and scaling vectors and what that means geometrically. So let's first look at this example of u and v, u being 1, 3, v being 2, 1. These are vectors in R2, so we can put them in the plane. The vector 1, 3, if we put it in standard position, starting at the origin, corresponds to this vector, that red one. And the vector 2, 1, the blue one down here. Now, we think about adding these vectors algebraically. This is a pretty easy thing to do. We have the vector 1, 3. If I want to add it to the vector 2, 1, I'm just going to add the corresponding parts of those matrices. So I'm going to add the first entries. 1 plus 2 will give me 3, and 3 plus 1 in the second entries would give me 4. Give me the matrix 3, 4, which is exactly this matrix this vector that I drew. This black one, u plus v is 3, 4. Thinking about this algebraically, and the title of this slide is the parallelogram rule for addition of two vectors, is that if I have two vectors and I draw a parallelogram with those, the diagonal will correspond to the addition of those vectors. What's important here is, again, the positionless aspect of vectors. This vector v, starting at the origin and going to this terminal point 2, 1, I could draw starting at the point 1, 3 and going to the point 3, 4. This is another copy of that vector v. Same thing with u. If I start that at the origin and go to the point 1, 3, well, that's the vector I had in standard position, but I could instead start it at 2, 1 and go to that point 3, 4. And again, that's another copy of that vector u, just in a different position. And if I do this head to tail kind of placement of the vectors, I start one of the vectors at the terminal point of another, I get this nice parallelogram, and the diagonal of that parallelogram is the addition of those two vectors, u plus v. So that's the addition of vectors. Now we're going to talk about scaling vectors. Scaling vectors, or multiplying by some constant. So first, let's draw the vector 1, 2 in this plane. We're going to go over 1 unit, up 2 units, and it's always nice to start at the origin. So we're going to go up to this point right here, and the arrow is important as we're going in a direction there. So 1, 2, starting at the origin, going to the point 1, 2. This is the vector u. We're also going to draw 2u and negative 3/2 u. Algebraically, if you think about 2u, this is 2 times the vector 1, 2, and we're just going to multiply each of those entries. That's going to be 2, 4. And in the graph, 2, 4 is going to be this vector right here, 2u. And really what this is just scaling that vector, doubling the length of that vector. It has the same direction. We're just doubling the length. We could also multiply by some negative number, negative 3/2 u. Would give us negative 3/2 times 1, 2, which is negative 3/2 times negative, or over negative 3. That point down there, that would be negative 3/2 u. Going in the opposite direction, but it's still just going to be taking that vector, stretching it a little bit, and then flipping the direction. So what we just talked about is a linear combination of vectors. A linear combination is things that you can do by adding vectors and multiplying by scalars. So the definition is, given the vectors v1 to vp in Rn. We're just saying that these have n entries in these vectors. And given n scalars, scalars is just a fancy name for real numbers here. The reason that they're called scalars is because when you get into more advanced things, they don't have to be real numbers. They can be more complex things. So scalars is a more general term. We can think about them as numbers right now, C1 to Cn. The vector W, defined by W equals C1V1 plus C2V2 all the way to CPVP, is called a linear combination of the vectors V1 to Vp using the weights C1 to Cn. And this is a way that you can add vectors together with different multiples, a linear combination. So let's look at some examples of linear combinations of V1 and V2. We have 3V1 plus 2V2. Here C1 is 3, C2 is 2. We could have 1/3 V1. This would just be in the case that if you had a plus 0 V2, that's fine. There's nothing wrong with that. You could also be subtracting some values like a -2. And then an important one is this 0 right here is a linear combination. This is called the 0 vector. And this is just 0 times V1 plus 0 times V2. This is the vector with all zeros in the entry. And that is a linear combination of these vectors. If we think about V1 and V2, let's do an example. Let's say V1 is the vector 1, 2. Let's say V2 is the vector -3, 1. Now when I do this 3V1, should have little hats here, plus 2V2, that's going to give us 3 times 1, 2, plus 2 times -3, 1, which would give us the vector 3, 6. If we multiply the 3 there, the vector -6, 2. And if we add those together, would be a -3, 8. Okay, so linear combinations is different ways that we can add vectors together with scalar multiples. So now let's think about another example. We have two vectors, 2, 1 and -2, 2. And we're going to express each of the following as a linear combination of V1 and V2. We have this weird plane here with some weird grid lines. But we're just going to draw first V1 and V2. So V1 is the vector 2, 1, and that corresponds exactly with this line right here. This is V1, and V2 is going to correspond to that other line, -2, 2, is right here. So what these lines are going to be are different multiples of V1. So for instance, I could do 2V1, that's this vector right here. I could do 3V1, I could do 4V1 and everything in between. And I could go backwards too. Here's -V1, -2V1, -3V1, -4V1, and on and on. And since a vector is positionless, I could actually do that again down here as well. I could say that this is the vector V1, this is the vector 2V1, and on and on and on. And I could do here. Here's the vector 3V1, and onward. Similarly, I could do the same thing for V2. Here is the vector 2V2, 3V2, and onward. And here's the vector -V2. And again, since it's positionless, I could go into any of these parallel lines here. Here's a copy of the vector 2v2. Here's a copy of the vector negative v2. And on and on and on. So this nice grid line is just a nice way to add different vectors together, and we'll see all of that. I'm going to clear all these drawings so we can start again with this example. So here we go. We have the vector v1 again, and the vector v2. Now let's think about these four examples. Let's have 0, 3, which is going to be this vector right there. This is the vector A, 0, 3. How can I represent that as a linear combination of v1 and v2? Well, in one of our first examples, we talked about the parallelogram. And we do have a parallelogram here, and the diagonal of that parallelogram is A. So we could say that A is v1 plus v2. Another way to think about that is that if I take v1 and when I take the terminal point, I take v2 and do a head to tail kind of thing, where I end up is that 0, 3 point. Let's do the same thing now with B. B is negative 4, 1. That's this point right here. Here is the vector B. B is going to be the linear combination of, we can get there from doing a v2 vector, and we could do this vector right here, which is negative v1. So we have a v2 plus a negative v1 gets me to B. So plus a negative is minus. And then note that since addition is commutative, we could also think about this as negative v1 plus v2. That's fine. And then geometrically, that just means that we're going the opposite side of that parallelogram. We're going down first and then over. We could do the same thing for A as well. All right, I'm going to clear these drawings so I can do part C. C is a little bit tougher. We have the point 6, 6. Here's our vector C. How can I write that as a linear combination of vectors v1 and v2? What we're going to do is we're going to try to follow these grid lines to get to that point. I think the easiest way to do that, or one of the easier ways to do that, is to go on this v1 kind of line all the way out to here. That is 4 v1. And then we do a little v2 to get to that point there, v2. And we could say that C is 4v1 plus v2. For this example, let's double check that's actually correct. We do have 4 times 2, 1 plus negative 2, 2 would give us 8 minus 2, 4 plus 2. There's our 6, 6 as we need for C. So that does work out. Let's do one more. We have D here, 7, negative 4. That is this point, not there. 7, negative 4 is there. How can I get there? Well, we could do v2's, negative v2's all the way to there. So that is negative 5 halves V2. We're going 2.5 copies of V2. And then we could do 1 V1 to get to that point in the middle. So we could say that D is negative 5 halves V2 plus V1. We don't have to just have integers. We could have any combination of stuff in there. All right, moving on. Let's look at another example. Here we have 4 different vectors that we're going to look at. We have the vector A1 is 1, 0, 3. The vector A2 is 4, 2, 14. A3 is 3, 6, 10. And B is negative 1, 8, negative 5. And the question is, determine if B is a linear combination of those A1, A2, and A3 vectors. These are vectors that lie in R3, in 3 space, asking is it a linear combination. So we're going to say that vector B is a linear combination of A1, A2, A3 if we can find weights x1, x2, and x3. Those are numbers, those are scalars, numbers, constants, so that x1a1 plus x2a2 plus x3a3 is equal to B. Another way to think about that is, since these are vectors that we're dealing with, this could be x1, this is the vector equation, times that vector 1, 0, 3 plus x2 times that vector 4, 2, 14 plus x3 times the vector 3, 6, 10 is equal to the vector negative 1, 8, negative 5. This is our vector equation here. This corresponds to a system of linear equations. What we're saying here is if I have 1x1 plus 4x2 plus 3x3, this should equal negative 1. That is looking at all of the first entries. So x1 plus 4x2 plus 3x3 is negative 1. The second entries, we have 0x1 plus 2x2 plus 6x3 is equal to 8. 0x1 plus 2x2 plus 6x3 is equal to 8. And then finally, 3x1 plus 14x2 plus 10x3 is equal to negative 5. This is a corresponding system, and now we've finally related it back to section 1.1 and 1.2. When we're talking about vectors, in this linear combination question, we are talking about a system of linear equations. And we know how to solve this. We can solve this by putting it into the corresponding augmented matrix, row reducing, and then we can solve. So the corresponding augmented matrix looks at the coefficients. We have this bar for the equal sign, and then we have our B. Remember that the columns are associated with the variable. So this is going to be the variable for x1, the variable for x2, and the variable for x3. Note that this is also corresponding to the vectors a1, a2, a3, and b. And if I row reduce that, I'd have to do a negative 3 row 1 plus row 3 into row 3 and do some other things on top of that. I get this row reduced echelon form, that allows me to solve this very quickly. This says that x1 is equal to 1, x2 is equal to negative 2, and x3 is equal to 2. This is saying that these numbers, if I plug it into this equation, if I take negative 1 times that first vector, minus 2 times that second vector, plus 2 times that third vector, should equal the vector negative 1, 8, negative 5. That was a very important example that we just did, so we're going to look at it in a couple different ways. We have the vectors A1, A2, A3, and B are columns of the augmented matrix. Remember, that's what we just said right there. The columns are those three vectors. We have this bar for the equal sign, and then this special vector B at the end. So bringing it all together, the solution to this linear equation, remember this is a linear equation here, is found by solving the linear system whose augmented matrix is A1, A2, A3 times B. We're going to put the vectors in the equation, but that's the exact same thing as just having this kind of vector just written in a nice easy way with that vector notation. So everything we learned in 1.1 and 1.2 is now important as we're talking about solving a linear system, is asking a question, are those vectors a linear combination, or is the vector a linear combination of other vectors? So a vector equation, x1a1 plus x2a2 all the way to xnan, sorry, that should be xnan, is equal to B, has the same solution set as the linear system whose augmented matrix is A1, A2 all the way to AN, bar B. That's just in general what I said before. And one last thing, in particular, B can be generated by a linear combination of those vectors if and only if there is a solution to the linear system corresponding to the augmented matrix. If there is a solution to the linear system corresponding to the augmented matrix. That means that the linear system is consistent. It has a solution. So what question we're going to be answering in some next examples is a linear system consistent? And that's going to go to reducing a augmented matrix to echelon form or reduced echelon form to figure out if a system is consistent. To help us out with this, and another important idea is to look at the span of a set of vectors. So let's look at this span of vectors, and we're going to start with an example in 3 space, this 3, 4, 5. Let's start by just sketching that vector, 3, 4, 5. That's going to be associated with going 3 steps in the x1 direction, 3 steps in the x1 direction, and then 4 steps in the x2 direction, 1, 2, 3, 4. And then 5 steps in the x3 direction, 3, 4, 5. If I kind of put those all together, I go over in the x direction, over in the y direction, up in the z direction. That's another way to think about x1, x2, x3. I get this vector that is the diagonal of this 3D box that I drew, V. All right, drawing in 3D is a skill that's definitely difficult to grasp. If you've taken a Calc 3 course, then you've already gone through the ringer on that, but it is important to kind of understand how these vectors work. All right, so that's how we draw V. It's the diagonal of a box, similar to how we can think about V as the diagonal of a square in 2 space, or not a box, but a rectangle in 2 space. Right, this is just the corresponding thing in 3 space as a box. All right, so the question asks us to label the origin V, 2V, and 3/2 V on the graph below. So V we already labeled. The origin is a vector. That is the 0 vector. It's just a point right at the origin. 3/2 V is going to be the next one. That's going to start from the origin. We're going to go in the same direction as V. But we're just going to keep on going 3/2 the length. And then 2v is going to be double the length of v right there. We could also go in the negative direction. It's a little bit tougher to draw in 3D, but here's maybe negative v. And we see that all these vectors, v, 2v, 1/2, or 1 and 1/2 v, 3/2 v, all lie on the same line in 3 space. And we're going to say that span of v is the set of all vectors of the form a constant times v. And here, the span of v is a line through the origin. So the span of v is all of the vectors CV, where C is a real number. Let's do this again. We have u, v, u plus v, 3u plus 4v on the graph below. Okay, here u is going to be this vector right here. V is going to be this vector right here. So here's v, here's u. I'm not giving coordinates so much, but these are things in 3 space, u and v. If I wanted to graph u plus v, that would be the diagonal of this parallelogram right here, u plus v. Again, I could get there by taking u first and then taking v to get there, or taking v first and then taking u. It's the diagonal of that parallelogram. If I wanted to get to 3u plus 4v, I could go out 3 steps on that plane in the u direction. There's 3u. And go out 4 units in the v direction, 4v. That would give me this vector 3u plus 4v. Now we could do this for any kind of linear combination of vectors, especially one that we already can write down. This is the 0 vector right there. And we have that u, v, u plus v, 3u plus 4v, 0, all of these vectors all lie in the same plane. And we say that the span of 2 vectors here is the set of all vectors of the form x1u plus x2v. x1 and x2 are scalars. And in this case, the span of uv is a plane through the origin. Has to go through the origin because 0 is a part of that as well. It is all the linear combinations of those vectors. So let's define span formally. Suppose we have p vectors, v1 to vp and Rn. Then the span of those vectors is going to be given by span of v1 to vp. And that is going to be the set of all linear combinations of v1 to vp here. Stated another way, the span of v1 to vp is the collection of all vectors that can be written as x1 v1 plus x2 v2 plus dot 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 plus xp to vp. That's a linear combination of those vectors where x1 to xn are scalars or constants or real numbers in our case right now. That is the span. It's all linear combinations. We're seeing in this section that linear combinations are related to linear systems. Linear combinations are going to be important. In fact, they're fundamental to this whole course, linear algebra. So a new example. Let's have v1 is 2, 1, v2 is 4, 2. We are in R2 right now. Let's find a vector in span of v1 and v2. There are infinitely many. We could do a whole bunch. Let's do v1 plus v2 is in the span. That would be 2, 1 plus 4, 2 would give us 6, 3 is in the span here. We could do all different kinds of combinations. Here's another vector in that. You could have 1/2 v1 plus pi v2 would be another vector in that span. It doesn't have to be just nice constants. We could have any kind of constant in there as well. But the goal here is to describe the span geometrically. We saw on the previous page that the span of two vectors here was a plane through the origin. In this case, that is not going to happen. The span here is going to be a line through the origin. And the reason that is the case is because v2 is a constant multiple of v1. So we could think about the span of v1 and v2, not plus, v1, v2 is the same as the span of just v1. And that would give us a line. All right, let's take this example of 1/2 v1 plus pi v2. I could write that as 1/2 v1 plus pi times 2 v1. And all of a sudden, this is now just a constant times v1. No matter what thing that you put as a linear combination of v1, v2, now you could just write down as a constant times v1. Could be crazy constants, but they're just a constant times v1, and this would be just in the span of v1. So just because we have two vectors does not necessarily mean that we have a plane geometrically. We have to think about if they're constant multiples of each other. Let's say that a little more carefully. Let's look at spanning sets in R3 in 3 space. If we have two vectors, v1 and v2, we say v2 is a multiple of v1, then the span is just going to be the span of just one of those vectors, either one, and that's going to be a line through the origin. That's like what we just did in our previous example. No matter what kind of multiple I take of those, everything's just going to lie on that line, including the origin itself. If they're not multiples of each other, v2 is not a multiple of v1, then this span is going to be a plane through the origin like we saw in that previous example. So next example here we have v1 and v2, two vectors in R3. The question is the span of these two vectors a line or a plane? The question that we're asking is v2 a multiple of v1 or is v1 a multiple of v2? Same question either way. And we can see that if this is going to be a multiple, that means that I need to have some number c times 4 has to equal 6. That would be c is 6 divided by 4, 3 halves. Okay, that's always going to be the case, but then that same number has to be the same for c times 2 has to equal 3. It's looking at these digits right here. And for the third digit, same thing. And again, we get the same value, 3 halves. So that just verifies that if I take 3 halves times v1, I get v2. That means that the span of these two vectors is just going to be equal to the span of one of those vectors, either one, and that's going to be a line through the origin. Let's do that again. We're in 2 space this time, v1 and v2. Is this span a line or a plane? And the question we're asking is, are those multiples of each other? Well, if they are multiples of each other, that multiple would have to be times 4. To get to -1 to -4, it has to be times 4, but that doesn't work down here. This says that our multiple has to be 1/2. Those don't match up, so therefore this can't be a constant multiple. V1 and V2 are not multiples of each other. So this means that the span is going to be a plane. And it's important to think about when we're talking about 2 space, this plane is the xy plane or the x1, x2 plane. No matter what vector that I put in here we'll have -1, 2, and -4, 1. These 2 vectors here, I could get any point in the plane by a linear combination of those vectors. Might have to add and subtract those vectors and use kind of crazy constants, but I can get to any point in the entire plane with those vectors. So last example here, we have a matrix A, 1, 3, 0, and 2, 1, 5, and a vector B, 8, 3, 17. And the question is B in the plane spanned by the columns of A? That's going to be another way to think about it is, does there exist scalars x1 and x2 such that x1 times the first column, 1, 3, 0, plus x2 times that second column, 2, 1, 5, would that be equal to 8, 3, 17, that vector B? This is similar to a question that we've answered before. If we think about these vectors as A1, A2, and B, then we're just answering the question, is there a solution to this linear equation? And we can do that by setting up a system of linear equations, which we kind of already have, and put it into an augmented matrix, and then row reducing and solving. So the corresponding augmented matrix is just having the matrix A followed by the B, and that's going to be our discussion even more in the next section. But we have our matrix 1, 2, 3, 1, 0, 5 bar, and then the matrix, the vector B. And if we row reduce, the row reduction would be -3 row 1 plus row 2 into row 2 to get this 0 right here. And we could also do a row 2 plus row 3 into row 3 to get a 0 here. We get this in, this is row echelon form. And we see that we have a problem. We have this row 0, 0, -4. This corresponds to the linear equation 0 equals -4, which is a problem because that doesn't work out. So this is an inconsistent system. We said before that if there's an inconsistent system, then there is not scalars x1 and x2 such that this linear equation is satisfied, that B cannot be written as a linear combination of A1 and A2, and putting it in a slightly different way, this means that B is not in the plane spanned by the columns of A. B is not in the span of the vectors A1 and A2. We're going to continue talking about this kind of vector equation, this A and B, in the next section in 1.4.